Let's explore the science of energy. Station 1, Part 1. This activity goes along with Need Science of Energy kits. Each Science of Energy kit comes with materials for the activity, but you may need some common household or classroom materials. For this activity, you'll need the SUPERBALL, any common scale, 1 meter tape measure. This activity will explore the transformation of energy that takes place when you drop an elastic ball from a certain height. Have you ever noticed that the ball doesn't bounce all the way back up? Let's figure out why. Energy always transforms from potential, how it's stored, to kinetic, how it's being used. Since we're talking about elastic balls, we're going to talk about elastic energy. This is energy stored in objects that are stretched and compressed, such as springs and rubber. As a bouncy ball collides with a surface, most of its energy is transformed into elastic energy. That's because most of its energy goes into compressing or transforming the shape of that ball. When this collision occurs, some of that energy is wasted or dissipated through sound or thermal energy. A bouncy ball is dropped from a height, so gravitational potential energy plays a factor. This is energy stored by lifting or storing an object off of ground level. The total amount of gravitational potential energy is determined by the height of the object off the ground, the mass of the object, and certain characteristics of gravity here on Earth. This energy is going to be stored a couple of different ways, and it's going to be used a few different ways. When a bouncy ball is falling or bouncing upward, it's using motion energy. This is the amount of energy required to move an object. The amount of motion energy is always determined by the mass of the object and how fast that object's moving. When a bouncy ball hits a surface, not only does that energy transform into elastic energy, but it dissipates energy in two very important forms. The first is thermal energy. This is energy in the form of heat. Collisions and friction create thermal heat. Try clapping your hands together. Eventually they get warm. Just like when the bouncy ball hits the surface becomes warm. The reason you can hear your hands when they clap is because you're releasing sound energy. This is energy in the form of sound waves. Thermal energy and sound energy are not the intended energies of a bouncy ball. Thermal energy and sound energy, in this case, are called dissipated energy. This is an energy that's destroyed, but it's energy that's wasted. It's not used for its intended purpose of bouncing the ball up and down. In this lab, you'll drop bouncy balls from a given height and measure their recovery bounce height. This will help you calculate the percent of energy recovered during the bounce. Follow these steps to collect your SUPERBALL bounce data. 1. Measure the mass of the SUPERBALL and record it in the data table. Use a small measuring cup to keep the ball from rolling off, but remember to zero the scale. 2. Drop the SUPERBALL onto a hard surface from a height of 1 meter. 3. Measure the SUPERBALL's rebound height. 4. Repeat steps 2 and 3 for 2 more trials. One person drops the ball, one person measures the height. 5. Calculate the average rebound height and record it in the data table. The scale will give you the ball's mass in grams. You need it in kilograms. So we need to transfer from grams over to kilograms. We start at the basic unit, gram. To get to kilograms, that's 1, 2, 3 places to the left. 3 place values to the left. So if the mass from the scale was 16.3 grams, I move my decimal 3 place values to the left. If I leave a gap, that gap gets replaced with a 0. Wherever my finger, pointer, pencil ended, that's where the decimal ends up. So 16.3 grams is about 0.16 kilograms. You'll measure the rebound height 3 times, and then you'll add up those 3 trials and divide by 3 to get the average. My average in this case is 0.37 meters, or about 37 centimeters. In order to build some conclusions about this data, we need to understand the gravitational potential energy formula. Gravitational potential energy is measured in joules. Joules is a measurement of energy, kind of like calories. Earlier we discussed that gravitational potential energy has to do with the object's mass, its height off the ground, and Earth's gravity. So those are the same formula variables we see here. The object's mass, always in kilograms. 9.8 is Earth's gravitational force constant. And then we're looking at the height of the object being held off the ground. You'll not only be using this formula to calculate the initial gravitational energy, but you'll be using this formula to calculate the total gravitational energy. Once you let go of that ball, no energy is added, so all energy is conserved. It just changes forms. To help make sense of this transformation of energy, let's use something visual, like a pie chart. These pie charts can show us not only what forms of energy are present, but the relative amounts. At position 1, the SUPERBALL is being held off the ground. It's not moving, it's just off the ground. So all of its energy is being stored as gravitational potential energy. At position 2, it's halfway down to the ground. So we have half gravitational and half kinetic energy. It's at half its height, so half of its gravitational energy has been used. That's why the other half has to be kinetic energy. The only other thing that it's doing is moving. At position 3, we're looking at the object right before it hits the ground. So the only thing that it's doing is moving. It's not off the ground, so it doesn't have any gravitational energy. It only has kinetic. If we let the ball hit the ground, we'd actually be looking at elastic energy, the energy that's stored by that compressed SUPERBALL. When this happens, that total amount of energy, which never changed, transforms mostly into elastic energy to compress the ball, but the rest is dissipated through thermal energy by the collision and sound energy created by that collision. Because every single one of these pie charts includes the same total amount of energy, that dissipated energy isn't destroyed, but it can't be used again. It's been dissipated. It's been thrown out into the universe. The potential elastic energy at the bottom becomes our total gravitational potential energy at the top. That dissipated energy acts like a gallon of gas. Once it's used, it served its purpose. That energy wasn't destroyed, but we can't use it. This is why the bouncy ball doesn't bounce all the way up. It dissipates or loses energy at the bottom. Now that we've looked at this qualitatively and understand what forms of energy exist at each point, we can start looking at it quantitatively and add our numbers in. Once we understand the forms, we can apply the formulas at each position. Position 1 is all gravitational potential energy, so we can use the gravitational potential energy formula. If my bouncy ball had a mass of 0.02 kilograms and was dropped from a height of 1 meter, I would have a total gravitational potential energy of 0.196 joules. This is also my total energy, which means that every pie chart at every point throughout that motion has 0.196 joules of energy. Position 2 splits that energy amongst gravitational and kinetic energy. So we know that the gravitational potential energy is determined by the height, in this case 0.5 meters. So we only have 0.098 joules of gravitational potential. We know that the total energy is composed of the gravitational and kinetic energies. We know the total, we know the gravitational, so using a little one-step equation, we can solve for the kinetic energy. What's happening to that variable? We're adding, so we subtract from both sides. Both the pie chart and the equations confirm that half the energy is gravitational, half the energy is kinetic. At station 3, we assume all of that gravitational energy at the beginning became all of the kinetic energy at the end. So if we started with 0.196 of total gravitational energy, we end up with 0.196 of kinetic energy. So our total kinetic energy is 0.196 joules. This is how the energy is being used right before it hits the ground. Once it hits the ground, it turns into elastic energy. That collision also dissipates some energy. This is why at position 4 we have about 25% of our energy as dissipated. It was given off as thermal or sound energy. We can calculate how much gravitational potential energy exists by using our average rebound height. Using the order of operations and this example data, we find that it's 0.147 joules. To keep the total amount of energy the same, we had 0.147 joules of gravitational potential and 0.049 joules had to have been dissipated. This dissipated energy happened when the ball collided with the ground, and it explains why the ball doesn't bounce as high. We can find how efficient that bounce was by calculating the percent of energy recovered. We do this by taking the gravitational potential energy at position 4 divided by the gravitational potential energy of position 1 times 100. Plug in our given information, use a little order of operations, and we found that this ball ball is 75% efficient, which is why it bounced to 75% of its height. Follow these same steps for your super ball and the two black spheres. Analyze all three drops the same way to build your conclusions using the data you collected.